In this lecture, we're going to explore the Fourier series and Fourier transform. So first of all, let's talk a little bit about the frequency domain and what we mean when we say a frequency domain. Now, in previous chapters, we've discussed the concept of probing a signal using a cross correlation. So complex signals, like an EEG signal, can be analyzed by comparing them with reference signals. So a cross correlation, as we've seen, provides a running comparison between the original signal and a reference signal. So cross correlation could be used to find simple signals like sinusoids that are embedded in a complicated signal. For example, if we cross correlate an EEG signal with sinusoids that have frequencies we think might be embedded in the signal, we would get an indication of how much of that sinusoid was present in that signal. So for example, you can see in the top figure here we have an EEG signal, and then this is our reference sinusoid of 2 Hertz. We then cross-correlate the EEG and 2 Hertz, and the cross-correlation function looks like this. If we now do that for several frequencies, let's say 1 to 25 Hertz, then we get a plot. Basically, if we plot the maximum correlation value as a function of frequency, we get a plot that indicates the amount of different frequencies present. So for example, in this figure, right about 7 Hertz appears to be where our maximum energy of our signal is concentrated. So we would have a lot of 7 Hertz signal present in this particular EEG data. Probably the easiest way to do that is to not do an endless number of cross correlations, but rather to do a spectral analysis using the Fourier transform. So a lot of signals are more useful when you view them in the frequency domain, which is the last plot we looked at on the previous page. And determining the frequency content of the waveform is called spectral analysis. Basically, spectral analysis takes a time domain waveform and it decomposes it into its frequencies. And this is analogous to thinking about how a prism would decompose light into its spectrum of colors. Various techniques are used to convert signals into their spectral equivalent, and these have different strengths and weaknesses. And basically, we can divide these into 2 categories, the first being the Fourier transform, and the other being more modern methods such as those based on models of the signal source. What are some of the limits of spectral analysis? Well, first of all, if you want really accurate spectral analysis, you would need a periodic, noise-free, and finite signal. If you have short segments and noise, then you only are getting estimates of the true spectrum, and it's important to keep this in mind. Intelligent spectral analysis requires an understanding of what spectral features are of interest. So 2 spectral features that might be of potential interest would be the following. First of all, what is the overall shape of the spectrum? In other words, what are the broadband features? This is termed the spectral estimate. Secondly, what are some local features in the spectrum, or narrowband features, that are sometimes referred to as parametric estimates? I'll give you an example. In EEG, you have a couple of different kinds of estimates that are made. Sometimes you're interested, say, in the average power over a band of 4 to 8 Hertz. Other times, you might be interested in a specific frequency associated with muscle movement called a mu rhythm. And this mu rhythm occurs over a 2 Hertz bandwidth. So that would be a more narrow band frequency within a larger frequency characteristic that we might be interested in for an EEG signal in certain cases. So here's an example of the spectrum obtained from a waveform that consists of a 100 Hertz sine wave and white noise. The waveform isn't shown here, but basically the spectrum is produced from 2 different methods. First, just taking simply the Fourier transform. And so here's the MATLAB output when we take a Fourier transform. And you can see here at 100 Hertz, there's a clear spike that would indicate there is sinusoidal energy there. But if you look then, we have all these other spikes mixed in throughout the signal. And so we know, because we created this signal, that those are just noise generated. If we then use an averaging technique, This flattens out the signal, but notice that the clear peak at 100 Hertz is missing. So while we could tell that there might be a little more energy focused around 100 Hertz, it's not clear that it's specifically at 100 Hertz like it is in this figure. However, in this figure, the figure on the left, you have all these other components and you don't know if they're real or if they're just noise. So basically, Fourier series analysis is the first step in understanding the Fourier transform. A Fourier series analysis can only be done on a periodic waveform. And it's basically a harmonic sinusoidal decomposition. So if we think about a single sinusoid has a single frequency. So the energy is all concentrated in one frequency. What sinusoidal components of a signal do is they map directly onto the frequency components of a signal. So here's an example of a single sinusoid with frequency 2 pi mf. And this particular case, we've basically correlated, this is a 10 hertz sinusoid. So by correlating that with 10 hertz, we get in the frequency domain a magnitude that is centered at 10 hertz and doesn't really have any signal width because it's a perfect correlation. In the phase, we also get a phase that shows up at 10 hertz as well. So basically, if we look, here's an example of a triangle type wave. If we now decompose that into its Fourier components, we find that they kind of look like this. And then if you plot the magnitude of each of these components as a function of frequency, you find that the plot looks something like this. This is what we refer to as convergence. Notice the amplitude of the higher components is getting smaller and smaller, meaning that we don't need that many components to accurately represent this particular function. So the Fourier series analysis basically uses a sinusoidal bridge approach to find the spectrum of a periodic waveform. The Fourier series theorem states that any periodic waveform, no matter how complicated, can be decomposed into sinusoids that are the same as or multiples of the waveform's base or fundamental frequency. In other words, any periodic signal can be represented by sinusoids that are harmonically related to the fundamental frequency of the signal. Now, biological signals usually aren't periodic, but they can be taken as periodic for purposes of analysis. So here's an expression of the Fourier series theorem. F sub 1 is called the fundamental frequency. It's 1 over the period. And so our fundamental sine and cosine waves can be written as functions of F1 or the period t, or as I've done in some of my notes, omega 1, where omega is the frequency in radians per second. And then we can write the series as the expression given here. So this is referred to as the basis or reference family of the Fourier series. And m is an integer that indicates which level or which member of the family is present in that particular function. Now we can find the coefficients a and b by correlating the basis function with our function or our data set. So here's our function or our data set. Here's the sine function and cosine function, and that allows us to solve for the a's and b's. This is normalized with respect to 2 over t, so that as we integrate over the period, we have the 2 over t here. Now, you can find these, if I go back a page, you can actually find those from this equation. So if I were to take this equation and multiply the entire equation by the cosine of 2 pi n f1t, then I would find that with the exception of one term, all of the integrals are orthogonal or integrate out to 0. And so the only term remaining would allow me then to use the principle of orthogonality and solve for the coefficients. And that's the more common way of finding AM and BM. And you can also find a sub 0 that way as well. So if we were to implement this on a computer, then basically this goes from a continuous to a discrete format where you're correlating these discrete cosine functions, and there would be n of them, with the data set. So sometimes it's actually easier to think about the discrete Fourier transform by using the Fourier series as an example. So this is what your computer actually will do when it takes a discrete Fourier transform.